I got a couple more things to say about geometric vectors. I want to talk about scalar multiplication, that is taking a real number and multiplying it by a scalar. Now, this comes out of the notion of addition because, for instance, if I think of, say, u plus u, I mean that should be 2u, shouldn't it? And the notion of u plus u is here's the vector u. I'm going to take that, copy it, and paste it, and say, all right, I have u, and then I have another copy of u with the initial point at the initial point of the second u at the terminal point of the first u, and so that gives me this longer vector now, which we're going to call this one right here, should be u plus u, and that's what I would call 2u. Likewise, if I wanted to talk about 3u, I'd take another copy of u, stick it in there, and that would now be 3 times as long. In the same direction, but 3 times as long, that would be 3u. You could talk about 2.5u, which would, go from here up to there, or 17u, which would go from here up to, well, 17 times as long as u is. There's also the notion of multiplying by negative numbers. So for instance, if I wanted to talk about negative 2u, let's do this in green. Negative 2u would be pointing in the direction opposite of u, but still the length of 2u. So this might be negative 2u. Okay. Sometimes I forget to put the little hats on the u, but anyway, read it in context. So the definition here is k times v, where k is a real number and v is a vector. K times v is a vector with length, absolute value of k times the length of v. So you multiply the length by k, or absolute value of k. And the direction is the same as v if k is greater than or equal to 0. And the direction is the opposite of v if k is less than 0. So just opposite direction just means turn it around. Again, we haven't really defined what direction is, but you read the book what the direction is. The direction of a vector is the direction that it's going in. It's like, what? I don't see how that's a definition, but anyway. Multiply a vector by a scalar. It just stretches the length by a factor of whatever the k is. Changes the direction if k is negative. In particular here, we have a theorem that will tell us that the additive inverse of v is negative 1 times v. Right? Because negative 1 times v, if this is v, negative 1 times v is something that has the same length as v, but points in the opposite direction. Minus 1 times v. Well, that's precisely what we were calling negative v. Okay. Now, I guess this is also a theorem that addition is commutative. We've talked about this already, or in the previous video, that if you take u plus v and look at this vector that you get starting at the beginning of u and ending at the end of v, or if you do v plus u, you're going to end up in the same place. Starting here, ending there, you're talking about that vector across the middle. Either way, that red vector through the middle is u plus v, but it's also v plus u. Right? They're equal to each other. Addition is associative. This one, the picture gets a little more complicated, but let's see if we can do it. Associativity is something that looks like this. If I have u plus v plus w, I claim that that's the same as u plus v plus w. Now with matrices, we had to be careful about the order, particularly when we were multiplying. But vectors, just adding vectors, you can do them commutative. But you can also regroup them like this. Now to see a picture of that, if I've got 3 vectors, here's u, here's v, and here's w. Then let's see what we do here. U plus v, so u plus v, so I'm going to do an extra v here. So there's u plus v, Trying to make that parallel to V and the same length, right? And I'm going to just make that whole parallelogram. I'm going to try to keep the sides the same color. So if this is a red U, then that's going to be a red U. So U plus V is the diagonal across there, okay? And then if I add W onto that, I'll dot that. That's U plus V. And if I add W onto that, that would be sticking this W here, and that would come out like this, okay? U plus V plus W is the thing that goes all the way across like that. That dotted one is U plus V plus W. Now look at U plus V plus W. Okay, so can I do this? V plus W. Let's see. Can I? Well, let's start again here. Here's U. Here's V. And here's W. So U plus W, no, sorry, V plus W. V plus W is V and then W's here, right? So V plus W is this diagonal going this way. And then you add U onto that. Right, that's U. So we started here, we did V plus W, and then we do U. So that's this going clear out to there. Now, I don't know that it's obvious from these two pictures that those are the same. However, if I do this and I say, here's the three vectors that I start with. These two we use to make a parallelogram. These two we use to make a parallelogram. Essentially, I'm going to make what looks like a squashed box. And if I do U plus V plus W, it gets me from here to the opposite corner of that box. If I do, sorry, this was U plus V plus U plus V plus W. Oh, and then over here I had to do V plus W, which is V plus W plus U. It still gets me over to that other corner. Okay? So that the community or the associativity of vector addition is really saying you're just working your way from one corner of a cube over to the other corner. It's just a matter of what path do you take. You're going to use U once, you're going to use V once, you're going to use W once. You're going to use W once, you're going to use U once, you're going to use V once, whatever. I think I said those in the wrong order, but the idea is you get from one side to the other, one corner to the other. So addition is associative. We will have another way of looking at vectors in the next video, but it turns out it has all the same properties of these geometric ones, and we sometimes really don't distinguish between the two. But this is the geometric interpretation. Vectors are directed line segments. They're little arrows.